for this session, Vincenzo Dimonte, who is going to talk about generic I0 at alpha omega.
Let me thank you, the organizers, for giving me this opportunity. So it's just after lunch, we are all sleepy. Let me start with a public service announcement. So every year, an indefinite number, maybe hundreds of, maybe thousands of new definitions are introduced in the mathematical atmosphere. This can be very bad. At a certain point, the mathematical environment will not be able to absorb all these definitions, and we will have all these concepts littering our world. So please take action, be careful. Next time you will introduce a definition in the word that the word can absorb it. Let's say it. I'm going to introduce a definition. I want to do it consciously. It's my opinion that this definition can be absorbed by the current set theory world because it's connected with many different fields, and it's my opinion, and I wanted to show to you that it will be useful. So this is divided in two chapters. The first chapter is about just talking in general about the generic ranking to rank, why there can be important. And the second, in this case, it's more about the combinatorial of the first omega cardinals. Second chapter, I will be more specific about generic I0. And this is about choiceless combinatorics around alpha omega. Okay, so combinatorics, what do I mean by this? This is an example, the Chang's conjecture, that I'm sure most of you know. Every model of type Aleph2, Aleph1, that is, the universe as cardinality Aleph2 and there is a predicate of cardinality Aleph1 for a countable language, has an elementary submodel of type Aleph1, Aleph0. This is the notation. Okay, pretty much this says that if you have some relationship between Aleph2 and Aleph1, then this will be also between Aleph1 and Aleph0. I have an idea on why this makes sense, like a philosophical idea, because usually when people picture Aleph0, Aleph1, Aleph2, they picture like this. I've never seen anybody doing this, Aleph0, Aleph1, Aleph2. So this is my philosophical idea for why Chang's conjecture is true. Now you know why I'm a mathematician, not a philosopher. So, okay. This is a large cardinal. This is the consistency of a large cardinal, omega-1 Erdős, so pretty small. But there are many generalizations of this. For example, we can think about Aleph3, Aleph2, Aleph1 instead of Aleph2, Aleph1, Aleph0. Or we can have three things at the same time instead of one, so two predicates, and so on. This is much more than 1 omega-1 Erdős. So let me just introduce the large cardinals at the beginning. Kappa is measurable. Well, we know what it means, but one of the main definitions is that there exists an elementary embedding from V to an inner model M with the critical point kappa. This implies that M is closed under kappa sequences. This will be important. Now, okay, it's closed under kappa sequences. What about if M is closed under J of kappa sequences? Then the cardinal is called huge. I'm anticipating the next slide saying that what if it's called under J of kappa sequences, then it's too huge. J of kappa sequences is 3 huge, and so on. And this is formally what I just said. It's like this. You have this hierarchy. You start with measurable, huge, too huge, 3 huge. And well, what about omega huge? Let's close everything. Let's really close everything, like not only lambda sequences, but all the sequences where we just see in this morning talk that this is inconsistent under a choice. I forgot. This is important. Okay, so measurable huge, huge, 3 huge, but once you get to the limit, you get an inconsistency. Now, large cardinals we know are really large, and this can be problematic if I want to talk about the combinatorics of Aleph omega, Aleph 2, 3, 4. Large cardinals at the beginning seems to be useless, but there is a trick. You can apply their properties to small cardinals, and this is genericness. So generic large cardinals are sort of a virtual version of large cardinals that holds in a generic extension. An example, like what it means to be generic measurable, this is a very famous property. So let kappa be a cardinal, I an ideal on the power set of kappa. Then the power set of kappa modulo I is a forcing notion. We can have a generic, and this generic will be a V ultra filter on the power set of kappa. So we can make in the generic extension an ultra product, and we have J from V to the ultra product. This is still not, because maybe the ultra product is not well founded. We say that I is precipitous if the ultra product is well founded, and this is like a measurable, J from V to M. The difference is that M is not submodel of V, but of E of G, of the generic extension. In this case, kappa can be very small, can be Aleph 2, maybe Aleph 1, well, I don't know. Can be very small. So we have something like measurability, but for small cardinals. In the same way, we can extend the definition to all the large cardinals that I said before, even more. We can have generic supercompactness, generic huge, generic n huge. The same way, we can ask M is closed under sequences. Okay, so now I can go back to Chang's conjecture, to this Chang's conjecture. So the theorem is that a huge cardinal implies this extension of the Chang's conjecture. But in fact, it's a theorem in 2 parts. The first part is from a huge, you can have Aleph 2 that is generic huge. This is the difficult part. It's pretty complicated. Well, okay, a lot of time passed, so now it's not complicated anymore. It is. On the other hand, if we have a generic huge, we have the extension of the Chang's conjecture. So, well, let me write it down for the future. Oh. So we have huge implies consistency-wise. Generic huge. That implies, let me call it 2 Chang. Because in fact, here there is Aleph 3, Aleph 2, Aleph 1, but we can, like if Aleph 3 is generic huge, we can have Aleph 4, Aleph 3, Aleph 2, and so on. We can have pretty much a lot. In fact, in the same way, if we have n huge, generic n huge, we can have the long Chang's conjecture. I'm going to write it down. So if we have generic 2 huge, we can have the 3 Chang. And so on. If you have a 3 huge, you can have a 4 Chang. Okay. I want to underline that these are Aleph 1, Aleph 2, Aleph n. This is a very small combinatorics. The most practical thing I can think about if one can say practical about infinite cardinals, this is the best you can do. Then we can try to go on. So kappa is Johnson if every structure of cardinality kappa has a proper elementary substructure with the same cardinality. And this is it's implied by the omega chain. So we can put the omega chain here. That is, if aleph omega is if we have the omega chain, we can have that aleph omega is Johnson. And the consistency of aleph omega Johnson is a big open problem. It has been open for decades now. And you can see the problem.
In your notation, I think.
There is a wrong error?
Well,
there is two errors.
N is in the set of the aleph m's. And then it's aleph sub k.
Kn in omega.
You're right.
Omega, yeah.
Yeah, it's a problem in the notation. It's Kn in omega. Oh, okay, yes. I should have put either Kn below, yes. Yeah, what it means is just, thank you. It's just that, okay, this is the easiest way you can think of it, but you, instead of 1, 2, 3, 4, 5, you can have any ascending sequence of natural numbers. Okay. So what about, you see the problem here, because we can have huge, 2 huge, 3 huge, but we don't have omega huge. In fact, we don't have even generic omega huge. And that would be the natural way to prove that aleph omega is Johnson. So what can we do? Well, in fact, Kuhn proved with the same proof you can prove that there is no J from V lambda plus 2 to V lambda plus 2. So there is a little bit of space for this. These are called the rank into rank actions. We can have J from V lambda to V lambda, J from V lambda plus 1 to V lambda plus 1, these are stronger and stronger, and then J from L V lambda plus 1 to L V lambda plus 1. And now with the right forcing, I will tell something about it later, generic A1 or generic A0 at aleph omega do imply that aleph omega is Johnson because of this remark. So this can be a way to prove that aleph omega is Johnson. But I mean, I haven't proved it because it's still not clear how strong it is. The last theorem I know about this is a Foreman that probably proved this before I was born, that a 2 huge cardinal implies a generic 2 huge cardinal. So we can have 2 huge to generic 2 huge, but above we don't know. Of course, one can say, forget about it. Let's just consider generic large cardinals as hypotheses. We don't need to connect them to the rest of large cardinals. This is an opinion. But for now, yeah, I don't know how much strong it is. Okay, so let's go. So this is why generic rank to rank is important. It would prove aleph omega Johnson. So now let's define generic A0. It's much more complicated than I thought. The naive attempt is this. So there exists a J. Okay, disclaimer. I write LP aleph omega here instead of LV aleph omega plus 1 because it's easier to read. With GCH, they are the same. Okay. So the naive attempt should be exists J from LP aleph omega to the LP aleph omega of the generic extension. But you know, if you just do this, you're not going to prove anything.
But what are you assuming about the forcing? You say G is generic over some.
Yeah, for now nothing. This is why it's a naive attempt.
Huh?
This is a naive attempt. So I'm not assuming anything, and now I'm saying that you have to assume something about the forcing, and it's going to be the next slide. Because yeah, for example, if we have J from V to M, so this is what we know. If we have J to V to M, M is closed under critical sequences. So under sequences like a critical point. But if I is just precipitous, maybe we don't have this. we have this when I saturated. So you see that if we just pick, this is in general for all generic large cardinals, if we just pick them at face value, we lose lots of properties. So it makes sense. So what do we call generic immeasurable? Is precipitous or is saturated? I think it's okay, we can leave some space. If one wants to use generic measurable, must say exactly what it means. But then it's not just one concept, there are many. So this is the definition I give to generic A0 at Aleph omega. It's technical. I don't want to go through all the details. I'm just going to say that this is what you expect. This is the generic A0. This says that this is generic A0. This implies if we have this, then we have Aleph omega is Johnson. This is so kind of necessary to have Aleph omega Johnson. The rest are small things that if you know I0, you know you need these kind of things.
In the second point, what does that arrow mean?
Where?
So you have this pi being a map from...
Oh, surjection. Surjection. I mean, this means P is small. It doesn't add a lot of subsets of Aleph omega. You can think as an easy example the collapse of Aleph 3 to Aleph 2, for example. But the example you have to have in mind is this one. This is, if you think generic A0, you think of this one. Because in A0 you have kappa that goes to j of kappa, j of kappa, so on until a limit. And this would give you the same. J of Aleph n plus 2 goes to Aleph n plus 3, and so on, and until the maximum. Okay, so what can we prove with generic A0? So let me immediately say that if we have this, then LP Aleph omega does not satisfy choice. Okay, you can prove it. So when we don't have choice, sometimes we can measure how big is P Aleph omega anyway. We don't have choice, so it's not a cardinal. 2T Aleph omega is not a cardinal. And this is how we do. We just see what ordinals are more or less the same size of P Aleph omega. If you can surject P Aleph omega into an ordinal, it means that this ordinal is more or less the same size of us. So it's theta that is really measuring how big is P Aleph omega, more or less. Without choice, it's difficult. So this is the main theorem. Suppose we have generic A0, like I said before. Then in LP Aleph omega plus 1 is measurable. In fact, it's omega strongly measurable. Theta is weakly inaccessible, and theta is limit of measurable cardinals. Omega strongly measurable cardinals. So theta is definitely really, really big. It's a weakly inaccessible limit of measurable cardinals. And theta is measuring P Aleph omega. Now, confront this with the famous theorem by Scheller that we use in PCF theory, in fact, gives a very strict boundary to 2D Aleph omega. Now, this is with choice. This, without choice, is going to blow up 2D Aleph omega a lot. So it goes into a completely different direction. So pretty much, either generic A0 is consistent, and then PCF theory without choice cannot arrive to this. So there is some limitation on this. Or generic A0 is inconsistent. But then, usually, generic large cardinals are weaker than the large cardinal counterpart. So this would put some shadow on the consistency of I0. And nobody wants that, right? So, okay, this is why I think that if you remember just one slide, I think this is the slide to remember, that generic A0 is really in the middle of something. And so either it puts some limitation on PCF theory without choice, or it puts some limit, or there is something wrong in large cardinals. Okay. So, okay, I think I have time for introducing even a third way to think this. So having just alpha omega plus measurable is nothing new. It just it's an old result by accident. But this is weird. Theta weakly inaccessible limit of measurable cardinals. Where it comes from? It comes from determinacy. So let me just write d lambda instead of every time writing lambda plus is measurable and theta is weakly inaccessible limit of measurable cardinals. So L of R, when it satisfies AD, satisfies this. This is where everything comes from. Would improve that if you have I0, then we have the same. These are very close. And then this theorem proved that if we have generic A0, we have the same as alpha omega. When it does not have, so for regular cardinals with forcing one can keep is not really interesting. The interesting point is when lambda is singular. Now there is a theorem that if lambda is uncountable cofinality, then LP lambda satisfies choice, so it cannot satisfy all the things I said before. Then in the Mitchell-Stilkor model, if lambda is singular, then also LP lambda satisfies choice. So it seems something really rare, just think of lambda plus measurable and theta weakly inaccessible limit of measurable cardinals. So the conjecture by Woody, not by me, is that this is everything you can have. Either you use forcing, or if you are in some canonical inner model, then you can have this just when you have something close to I0. This is a third way to see these things. So now we have all the open problems. I mean, is generic A0 inconsistent or not? Can we prove generic A0 from A0? That would be great. Or in general, when we can have this d lambda, is it true that we can have it just for I0 or maybe another part? How small can be lambda? So with forcing, with using generic A0, you can push it down to alpha omega, but without this, how small can it be? What is the consistency strength of this? And so on. Also, please note this is my first topic where I'm not assuming I0. So this is that's it. Thanks for your attention.
Are there any questions? So let's take Vincenzo again.